All right, welcome back. We're going to pick back up from section 5.2 and then cover 5.3 and 5.4 as well today. So I'll start with the applications. One of the applications of exponential functions was compound interest. And so compound interest has this formula. The amount as a function of time is equal to P multiplied by 1 plus R over N all raised to the N times T. Now, if my morning class, this, if you're in my afternoon class, so this is new to you. But so the A of T is the amount in the account or owed, whatever it is that we're talking about, but it's the amount after T years. P is the principal, which is the amount that's put into the account at the very beginning, right? You go into a bank, you say, I want a savings account, here's $10,000. That $10,000 is your principal, right? R is an annual interest rate. And N is the number of compounds per year. Right, so typically we see things compounded monthly. If you have a bank account, every month they send you a statement that says, hey, you've got your penny of interest or whatever it is for this month. That's the compounds. So if you get it compounded every month, typical N would be 12. Sometimes they compound once a year, so N would be 1. Sometimes they compound every 3 months, right? Quarterly, so 4 compounds a year, that sort of thing. And then the last thing is that T is the time in years. So we have that. And if I were to walk into a bank and I deposit, let's say, $25,000 into a money market account that earns, let's say, 4.25% annual interest rate, and it's compounded, let's say, quarterly. And I can leave that in there for let's say I can leave it in there for 10 years. So how much do I have left in there? Let me just get this so it doesn't take up all the screen. Well, I can use that equation here. That equation, once again, was weird. There we go. The amount in the account is the principal multiplied by 1 plus R over N, all raised to the N multiplied by T. Right? So I'm just going to plug stuff in, right? It's asking me to find the amount that's in there after 10 years. So T is 10. I know P is 25,000. That's what I put in there. And 1 plus R. My R is 4.25%, but I want that as a decimal, so I'm going to write in 0.0425. Make sure we do that. And then n is, since we're doing this quarterly, n is 4. And we're compounding, n again is 4, and we're compounding this for 10 years, so times 10. So I just have to kind of step by step do the calculations. I'll start right here with 0.0425 divided by 4. Throw that in the calculator. I'm just going to grab a calculator here and throw it in. I get, oops, that's not what I wanted. 25,000 still, multiplied by 1 plus, and this division ended up being 0.010625. I can do this as well. 4 times 10, that's 40. The combination here is easy. It's 25,000 multiplied by 1.010625 to the 40, right? And then this calculation here is definitely a calculator thing. This number raised to the 40th power, right? So I'll plug that in, and it's definitely not going to work on that calculator. 1 point. I'm going to get a humongous amount of decimals here. In fact, the calculator that I have gave me this many before it said, I don't think you need any more than that. 1.5261, blah, 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 right? So yeah, I'm going to take this, and if I just leave this number in my calculator, I don't have to write it down. But if I just write down like 5 or 6 digits, I might be wrong in the end because I might have cut off too soon. So leave this number in your calculator and then just take that and multiply it by 25,000. And you can worry about rounding it in the end. So if I take that, multiply it by 25,000, I get 38154 and 12504. This number goes on, yada yada, forever, but I don't really care because we're talking about money, and they're never going to give you portions of a penny, right? So we would round it to the penny. That's that 2. Since the next number is a 5, I'm going to round that up. So my final answer here would be then $38,154.13, right? So one of the interesting phenomena, I don't know what the single of phenomenon, I don't know. Things that are interesting about math is in this function, I'm going to say a of n, because I'm just going to let n be natural numbers. Instead of like t being, I could actually have done this for like 1.5 years or 1.2 years or 1.06 years. I just want n to be just integers, really, but positive integers, so natural numbers, right? So if I change this formula up just a little bit, this a sub n is equal to, and I'm just going to say that my principal is 1, kind of just call it a base unit, so I don't want to throw in a principal just yet. But then if I have this 1 plus 1, r over n to the nt, right? And then one of the things that happens a lot in calculus is we say, let n run to infinity, right? What happens if you just let n go crazy and increase and increase and increase forever and ever and ever and ever, right? So, and I'm also going to let's just assume also that R is 1, right? So if I allow these two assumptions, I'm going to let n run to infinity and R be 1, then I have this 1 plus, I'm going to call it just 1 over n times t. I'm also going to, sorry, one more thing. I'm going to let t equal 1 as well. So we're just looking kind of at a snapshot unit, 1 year, 100% essentially growth, right? That's what we have. But if I have this, then I end up with this. And I'm letting n run off to infinity. And I'm not going to go through the proof as to what the next result is, how we get to that. But there is a little thing in the book if you want. I'll just steal it. The idea here is essentially we're just taking that rate of essentially 100%, and I'm going to let my time equal just 1 year. So we're just taking one small snapshot in time. But what happens if I keep compounding more and more times, right? Because if I compound more, then the interest that I earn from the last compound, in the next compound, I'm also getting interest on that interest, right? So it seems reasonable that the more times I compound, the more money I'm going to get. And then the question was, is there some limit to this? Or if I compound every day, do I get more money than if I did it every other day? If I compound every second, if I compound 200 times a second, where do we land here? And so let me throw this picture up here. They've done this calculations. Let's say we threw in $1 into an account that earned 100%. We threw it in for one compounding period, whatever, a year. After that first year, we ended up doubling our money, which makes sense because we had a 100% annual interest rate, right? But if we compound 2 times, I end up with an extra 25 cents out of that. Because of compounded, I got some money, and then we compounded again, and I got money, right, on interest. If we compound it 3 times, we get a little bit more. If we compound it 4 times, it's more. But you can see it's not growing. It's the difference between each of these is shrinking. And so here they've compounded it daily. If you compound it daily, you get an extra 71 cents as opposed to compounding it just one time per year. And if you compound it hourly, you're still at 71 and just a little bit more cents, right? And so the question is, well, what happens if we do allow n to go to infinity? And this, oops, my bad. This number ends up being this. Let me. Oops, that's not what I want. I want more digits. More digits, this. So here's a bunch of those digits. Right? If I allow n to go on bigger and bigger and bigger, sooner or later, I'm not going to change any of these digits, no matter how large n gets, right? And this number, there's a mathematician named Euler, and because his name started with an E, this number was given the identification of E, right? And so this number right here, Euler's number, is what happens if you allow these compounds to go without check. There is a limit to how much that will get you. But if we do that, if we let n run to infinity, right, then we call this a continuous compound. Right? And because essentially what happened is this expression right here is that number, right? I can exchange that for E if I want to. Oh, no, don't do that. If I want to compound continuously, which is to say an infinite number of compounds during any time interval, right? You're always compounding. Then I'm going to take this. I'm going to go back and say, well, our compounded interest formula was the principal multiplied by 1 plus r over n all to the n times t, right? And I end up with this r kind of jumps out, but to continuously compound, I think they call it, I'm not seeing it in the book right here, but they would call it, I think, still a of t, but then they have p times all of this junk right in here. If I'm allowing n to run off to infinity, ends up e raised to the r times t power, right? Let me double check, because I thought that's where the book was going. I was sort of looking at it, and it's not. So this is nifty, but nobody cares, at least yet, because we're not talking about it in the book. But at any rate, that's what happens. And so it does talk about in your book, though, exponentials with e's. And so if I have like e to the 4, right? I don't know what that is off the top of my head because e is this big horrific number, but I can plug it into a calculator, and your calculator should have this on it. But if I plug it in, I get this number here. And these numbers are going to be, they're irrational. They're going to go on forever. It'll stop. Your calculator will probably stop probably closer to this range, right? But that's it. Excuse me. That is, that's your e to the 4 is plugging into the calculator, and it spits out 54.598-ish, right? So if I wanted to graph this, I'm going to save the time because it's illustrated in the book, and that's not a bad thing to look at here. They do 2 at a time. And at this point, because, I mean, e is so ugly, this is definitely a calculator problem, but they've graphed 2 functions. The one was e to the x. And so they just took some x values. X is -2, -1, 0, 1, and 2. Taken e to the -2 and gotten a value, e to the -1, gotten a value, and so on and so on. And they've just graphed them, and you can see that e to the x is this exponential growth. They've plotted it there. And e to the -x, right, is essentially all of these values just swapped, right? And so it ends up being this exponential decay. It's just being flipped about the y-axis. All right. And then let's talk about horizontal stretching and vertical stretching here. So if I want to graph and I want to graph 2 things on the same plot. We'll do in red y equals e to the x. And let's say in blue, y equals, let's go 2e to the x. So I'm going to grab some x values. And I'm going to go e to the x in one, and 2e to the x in the other, right? So for my x values, we're going to just choose those -2, -1, 0, 1, and 2. I'll just throw them into a calculator because there's no way I would know what these are off the top of my head. But e to the -2 is 0.13. And I don't really care how accurate you get here, because when I graph it, there's no way I'm going to be more accurate than that first decimal place anyway. But e to the -1 is 0.37-ish. E to the 0 is going to be 1, because anything that's not 0 that gets raised to the 0 is 1. E to the 1 is just going to be e itself, which was that 2.718-ish, so 2.72-ish. And then e to the 2 is 7.39-ish. So if I graph this, let me get a graph. This one's not bad. All right, make it a little bit. So graph this. Well, I did it all in blue, which is super helpful. But I'm going to graph this in red, right? So I've got -2 and like 0.135 is like, I don't know, there-ish. -1 and 0.37, maybe there. 0 and 1. 1 and 2.7 would be somewhere like there. And then 2 and 7 point something, I don't know, there, right? So we can see the growth here. Something like that, right? Now in blue, I'm going to graph this guy, but I need values, right? And it's essentially, this 2 is just going to take whatever e to the x was and multiply it by 2, right? So I would have 0.27 here, and 0.74, 2, and 5.44-ish, and then 14.78-ish, right? So at -2, I have 0.27, which is, I don't know, there, maybe a quarter, a little more than a quarter up. -1, I have 0.74, so like there. At 1, I have 2. At 1, I have 5 point something, so up there. And then at 2, I'm way, way up there, right? And so if I plot this, it's not the best, right? But the point here is that if my y value is 1 on e to the x, then that y value is 2 on 2 e to the x. It's double, right? The distance that is right here is doubled for the blue one, right? This distance gets doubled for the blue one. Every distance everywhere, right? The distance right here, well, if you double it, you get to the other one. This is called a vertical stretch. Which is to say, I'm going to take that function and just stretch it up, or take everything and multiply it by a factor of 2, right? So it's a vertical stretch, and specifically on this one, it's by a factor of 2, right? And so whatever that number is in front of the exponential tells you this thing's getting stretched. If that number were, say, 1/2, it would not be a stretch. It would be a compression, because it's a number smaller than 1. And so everything would be compressed because you'd be multiplying it by 1/2, right? So that's a vertical stretch. The other thing that we'll see is, I'm going to still this. Oh, that's not helpful. I'm going to still this, because I'm going to use it again. Can I copy it? Did I copy it? Yay. All right. Okay, it's all just going to hang there. I'm just going to scooch out of the way. Now I want to graph. Let's go, and I'll try to stick with my colors here. Y equals e to the x. I should probably do that in blue because all of that's blue in my thing. Graph y equals e to the x. And I'm going to graph, let's say, I don't know, purple, y equals e to the 2x here, right? So I am cheating because I have all of these values. Oh, you suck. Why can't I move that? Not helpful. All of that. So I already have e to the x. I know those values, but now I'm going to find e to the 2x, right? And so like if x is -2, e to the 2x is e to the 2 times -2, which is e to the -4, right? And so that number is 0.0183. If x is -1, then I have e to the 2 times -1 or e to the -2. And e to the -2 was 0.135. If it's 1, then I have e, or sorry, if it's 0, then I have e to the 2 times 0, which is e to the 0, and that's 1. If it's 1, I have e to the 2 times 1, but that's just e to the 2. Throw that into a calculator, you'll get 7.39-ish. And then e to the, if x is 2, I get e to the 2 times 2, or e to the 4, and that is a lot. 54 point whatever, 6, doesn't matter. It's not going to be on my graph. It's humongous, right? And so if I graph this guy, grab this. And I'm going to graph, oh, don't do that. Stop it. I'm going to graph e to the x. I'll do, good thing I stuck with these color coordinated things and then whatever. Please forgive me. I'll do e to the x in blue. So I have that kind of same thing. I've got that -2 and like 1.135, -1 and 0.37, 0 and 1, and then 1 and 2.7, 2 and 7.39. So I don't know, somewhere up there, right? But I've got this. Looks like that-ish. I missed. Shocker. And let's do this. E to the 2x. Let's do it in red or purple. I don't know. Who cares? But if I plot these points, x is -2. Y is that very small number. If x is -1, I get 0.135. If x is 0, oops, I missed. Get that out of there. If x was -1, it was 0.135. If x was 0, I got 1. If x was 1, I got 7.39, so we're like right there, right? And then if x were 2, then I'm way the hell up there, right? And so what happens on this graph, I'm going to try to do this as carefully as I can. I come in below the graph until I swing through that pivot point, and then I'm above the graph. That's awful. Let me see if I can plot this in a better view of this. Yep, there we go. That's way better. Yeah. Yoink. All right, screw my graph, it's ugly. Look how beautiful that is, right? So this blue one's a little low res here, but this blue one is my e to the x, right? That's this. And then my purple one, look at that, they did blue and purple. How nice of them. Is that one, right? And they were even the same ones. That's amazing. But what's hard to see on this one is that the purple one is below the blue one until that pivot point, and then it shoots up, right? So that's important because this is not a vertical stretch, but it is a horizontal compression, right? You can see it better in my graph despite its ugliness. Oh, I don't know, maybe. But this point here just got squished in, right? This point here just got squished in, and this point, like say here, just got squished in. It all just kind of got squished inwards. And so we can generalize this and say that if I had e to the some number, a times x, and let's just assume that a is bigger than 1, then this is a horizontal compression by a factor of a. Now I'm going to throw one more graph on here. See if I can get this to look any good. I mean, sort of. I don't know if it'll show up very well, but here we go. Oops. All right. And you don't need, they changed it. They all of a sudden said, well, this may not be real, but it is. So don't worry about what this says. But e to the x here is in the blue, right? So we saw that from before. The e to the 2x is this compressed, this horizontally compressed one. But then I graphed one more in yellow, e to the 0.5x. So now it's the same. It's still this e to the ax, but now a is less than 1. And I want a to be greater than 0. Otherwise, we're talking about a reflection. But now if a is between 0 and 1, it's a stretch by a factor of 1 over a, right? And so if this like 0.5, that's like 1/2. And so it's a stretch of 2. And so any point here, right, the point that happens at 1 gets stretched. So now it happens at 2. The point that happens at x equals 2 is going to get stretched all the way over so that it happens at 4, right? So that's a vertical stretch that way. And they have this in your homework. They'll ask you what the stretches are, what the compressions are. This is how you figure out what those are. The graphing in the homework is not my favorite because it does it this way instead of saying, you know, find 2 points and figure it out that way. But you know, it's I guess not the worst thing in the world. All right. Anyway, that is E's, Euler's number E, and stretching and compressing in E. Let's move on. Let me clear this out. Maybe clear that out and get to 5.3. And 5.3 is now logarithmic functions. So the logarithmic function is the inverse of an exponential. There's I think it was an Italian guy that was dealing with exponentials, and he was like, this is really hard to do math in exponentials. So he essentially just devised the logarithmic function to get rid of the exponential so we could do math and then transform it back into exponentials after, because it's easier to work with them, maybe not written as exponentials, right? But let's look at this to start. If I have this function, this equation, x equals 2 to the y, right? And I wanted to graph this thing. First, I would note that it's hard to input x values, right? If I come down to my x chart, y chart, I don't want to start throwing in -2, -1 zeros, because right off the bat, if I say x is -2, that's 2 to the y. What is y? I don't know. So instead, what I want to do is throw in values for y instead. So I would throw in like 0 for y, because if x equals 2 to the, if y is 0, I know what that is. X is 1, right? What happens if y is 1? Well, then I have x equals 2 to the 1. Oh my goodness, that's 2. I know how to do this, right? What happens if y is, oh, I don't know, -1? Right? Well, if y is -1, I'm just plugging it in. That's 1/2. That's a half, right? So I can do these things. I can throw in values, but what is notable about this is that I'm throwing in my y values instead of my x values. I'm kind of going backwards with this. So in fact, the book has done more values. I'm going to just steal it because they look way nicer than what I write anyway. This thing out of my way. But they've done a few values. They chose y values, and then over here, they did a couple of values. Once they did those values, they then found the x values that coordinate. And once they did that, then they just wrote them down as ordered pairs, right? And once you have those ordered pairs, you can start graphing this stuff. And they do. So they've graphed this, right? The 0.10 is right there. The 0.21 is right there, and so on. And we see this kind of looks very much like an exponential, because it is. It's y equals, or x equals 2 to the y. But it's with those x and y's kind of reversed, right? In fact, if we look at the comparison of that graph with just scoot this down here, scoot this over here, get out of my way, make this bigger. I can't because I drew on it. Oh, see ya. That's helpful. I guess I don't need it anyway because it's already on the other graph, but here it is again, yoink. There's our graph. And if I compare that graph on this left plot with y equals 2 to the x, right? Just switching the x and the y here, you can see that they're essentially just reflected about that line y equals x, and they are inverse functions of each other, right? Because one of them is the reflection about that line, right? That makes this guy the inverse of that guy, and vice versa. So if I wanted to rewrite this y, x equals 2 to the y in terms of y, that's what this Italian guy did. And they said, well, I gotta call it something, so he called it a logarithm. I can't remember why, but to rewrite this, he just says that this is y equals the log, log for logarithm, and 2 was the base of the exponent. So 2 becomes the base of the log, which is written as a subscript under the log. And then it's the log of whatever's on the other side. So this is y equals the log base 2 of x. So you can say logarithm or log. And that's how you would say that. Y equals the logarithm base 2 of x. Okay. So that's essentially the way we can convert between an exponential and a logarithm. And I'll do a couple here. Let's say we have, let's say I have y equals 5 to the x, right? Then to write this as a logarithm, this is then whatever's up here in the exponent is now on the left-hand side of the equation. I have the log. The base was 5, and then it's the log of the other side, so y, right? So in general, we have this. Y equals a to the x is the same thing as x equals log base a of y. Right? So if I'm asked to evaluate a logarithm, let's say log base 9 of 3, I can use that definition. That definition is essentially this. That if I have a logarithm, it's the same as being able to turn it into an exponential, right? So if I have log base 9 of 3, I'm just going to say, I don't know what that equals and create an equation, right? And because now I've created essentially this equation on the left, which I'll rewrite just for the first couple of times, it's nice to see it in the same order. I'm going to write it as x equals log base 9 of 3. Because now I can go backwards and write this as this 3, which is in the log here, becomes isolated on the left-hand side. A is the base, so that's 9. And then it's raised to the x, which is, I don't know. I don't know what that x is. That's this guy, right? So how do I solve this? Well, I know 9 is 3 squared, so I can write this as 3 squared to the x. And then 3 squared to the x, I can rewrite as 3 to the 2x. And so I essentially have this, 3 raised to the 1 power is equal to 3 raised to the 2x power, and therefore those powers have to be the same. And then it would make sense then if I divide by 2, that x is 1/2. And let's see if that makes sense. If I plug in 1/2 into this equation, I'm suggesting that the log base 9 of 3 is 1/2. But to rewrite this, I get 9 raised to the 1/2 power is equal to 3. To rewrite that in my exponential, but that's true because 9 to the 1/2 power is the same as the square root of 9. That is indeed 3. What about, say, log base 2 of 8? Once again, I'm going to say, well, this is something, I don't know what it is, and I'll use this now newly created equation to rewrite this as an exponential. So that is 2 raised to the x power is equal to 8. But I know that 8 is 2 to the 3rd, and therefore x has to be 3. Right? Once I get 2 raised to some power is equal to 2 raised to some other power, the only way these are the same is if those two powers are the same. And so X has to be equal to 3. All right, you can do a couple of things in your calculator. There are some calculators that'll do every single type of log, but in your calculator, if you just kind of have a regular one that most people would have, you'll see either two buttons, either the log button or an LN button, right? Now this LOG is a log base 10, and this LN is the log base E, which we see a lot, right? And so you can take the log, if you're wanting to evaluate, say, just the log of 2, you can do that. You can plug that into a calculator. And here, I'll do it, log of 2 is somewhere around 0.301. So pause it here if you want for a minute, get the calculator out that you're going to use on test, throw in log of 2, and if this goes on, it's 3.301, 0.2999956, yada, yada, right? But you can also then evaluate, say, the natural log of 2, ln of 2, and you should get, I think it's 0.69 something, 3. Yeah, 0.69314, blah, 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 right? So make sure you know how to do those, right? Because you'll need to do those, but those are the two logs that you can find on your calculator. If you need to evaluate something like, say, up here, we had log base 9 or log base 5, but if you need to do it, say the log base 2 of 50, right? I don't know what that is, but there's a log change of base formula that says this. If I have the log base, let's say A of X, I can change this by saying that this is the log of, and I can pick my base, it doesn't matter. So I'm just going to use B for any base, it doesn't matter, of X over the log. I have to have the same base, so same B of A, right? So it's the log of whatever you're taking the log of initially divided by the log of the base in a new base where those bases are the same. So that is to say, if I have a calculator that can do the log base 10, I can turn this equation, that's not helpful, into the log of 50 divided by the log of 2, or I can change it into the natural log of 50 divided by the natural log of 2, as long as those bases are the same. If I really wanted to, I could say that this is the log base 21 of 50 divided by the log base 21 of 2. This is not particularly helpful, but I could do it. These things are all going to be equal. So take a minute and plug in log of 50 divided by log of 2, and then the natural log of 50 and divide it by the natural log of 2. In either case, you should get they should both be equal, and you should get somewhere around 5.643, something like that. Round up to 4.4. So again, make sure that you can do those in your calculators. But you would also want to, say, graph a couple of these. And again, since I'm just terrible at graphing on this tablet here, we're going to just kind of cheat and use the book's picture. But if I wanted to graph the natural log of X, what I can do is, there's two things that I can do, is I can just start plugging in X's, right? X is whatever you want, 0, 1, 2, 3. Start with maybe 0.5, and I'll show you why I'm starting there. But then like say 1 and 2 and 3 and 4 and 5 and so on if you really want more. The reason I'm starting at 0.5 is if I take the natural log of 0, if you have a calculator, throw it in, see what happens. But your calculator should get mad at you. And it should spit out something like error or domain issue or something like that, because you're never going to get a 0. You can't evaluate. You can't evaluate the natural log of 0, right? And so, and we'll show this on the graph. In fact, I'm just going to steal their chart here. They came up with these numbers. 0.5, they get this negative 0.7. At 1, they get 0 and 2. And then they graph it like this. Plotting those points, 0.5 and negative 0.7, 1 and 0, 2 and 0.7, and so on and so on. And the graph looks like this. But we can see, very much like the exponentials, we have this asymptote, but this asymptote is a vertical asymptote. You're going to get closer and closer and closer to that y-axis, but you'll never actually touch it. You'll never actually get to x equals 0. And you'll never be on the other side of it in the real number system, right? So when you go to graph these, make sure that you're paying attention to domain issues. The domain of a natural log or any log is 0 to infinity, not including 0. So it's parentheses there. You can't plug in 0, otherwise you're in trouble. It's not going to work out. And then, of course, with these guys, we'll kind of just go through this pretty quick, because we've seen it before. But if I want to graph y equals the natural log of x plus 3, because I have inside these parentheses this plus 3, this should be a horizontal shift of 3 to the left, right? Your horizontal shifts typically go against that sign. And so if I actually plug in values, find my x and y coordinate points, right? I end up with this graph, and you can see that it is just this graph over here that we just did, but shifted to the left 3 places, right? Instead of coming up like this, it's now just shifted to the left, and that's the exact same graph translated left 3 spots. Yeah. Well, I was going to ask if there's any questions, but I forgot. I'm not doing this live. Again, if you do have questions, feel free to email me. I will post responses in the discussion area of Canvas, most likely, so that I can use math type. But that's it, I think, for 5.3. So let's look at 5.4. And 5.4 is properties of logarithmic functions. So this is largely just ways of manipulating these, but the product rule is the first thing we'd look at here. So if I have the log base, whatever base, it doesn't matter. But if I have two things multiplied, inside that log. So it's the log of the product of x and y. I can break this up, right? I can call this the log base a of m plus the log base a of n. And that is because what we're dealing with is exponents. And so if I have a product of exponents, it should be the same as the sum of those logarithms of those exponents. So for example, if I have something like, say, something easy, even like log base a of 6, well, I can say that that's the same thing as the log base a of 2 plus the log base a of 3. Because 6 is 2 times 3, I can break that up. Right? You can test this out, pick an a, it doesn't matter. Just say the log, just pick a 10 if you want, of 6. Figure out what that is, plug it into a calculator, and figure out what the log of 2 is and the log of 3 is, and add those together. You're going to get the same answer on the left and the right as long as you put it into the calculator correct, right? So if I have, this is more useful in bigger expressions. If I have, like, say, the log of 9xy, well, I can write this as the log of 9 plus the log of x and plus the log of y. Broken them up, I can move them around if I need to, but that guy is definitely broken up. Oops. The next one is, oh man, knock it off. The next one is called the power rule. And the power rule comes from, I mean, it should be pretty obvious. If I have, like, say, log of y squared, well, this is the same as log of y times y. And using the above rule that we just used, I can then call this the log of y plus the log of y. But that's a log of y plus another log of y. That's 2 log of y's, right? And likewise, if I had something like, say, log of x to the third, I can break that up into the log of x plus another log of x plus another log of x. But that's 3 logs of x, right? And I can then generalize this into the log of whatever it is to some power. It doesn't matter what that power is. Let's call it b. And it also doesn't matter what that base is, right? The log base a of x to the b is equal to b times the log base a of x. Is essentially, and this is the power rule right there. It's basically, though, the product rule repeated over and over. So that tells me, though, that if I have something like, say, the log of x to the 25th, that's the same thing as 25 logs of x. And we have another property called the quotient rule. The quotient rule says that if I have the log, and again, the base doesn't matter, the log base a of, let's say, x over y, I can break this up into the log base a of x and then minus the log base a of y. And so one of the things that you'll see is a lot of times they'll say, like, what's the log of x over wx? Let's not use x, let's use wy. Well, if I use this product, or this quotient rule, then that tells me I have the log of x minus the log of that denominator, which is wy, right? But log of wy, I can use the product rule here, and so I end up with log x minus, but it's minus this, whatever's here, that whole thing is being subtracted. So when I break it up into the log of w plus the log of y, that minus has to apply to everything. So be careful. It's minus log w and minus log y, right? So anything in the denominator is going to end up with a negative in front of its log, and anything in the numerator is going to just be a positive, right? So something a little less ugly here. Log w, x, y, z. I can call this the log of w plus the log of x minus the log of y and minus the log of z, using both of those rules simultaneously. Okay. So that'll help us in solving things that look like this. If I have, say, the log of, say, base b, I don't know what that is, but of 64, and I'm subtracting the log base b of 16, I can combine this by going the other way with this quotient rule, right? The quotient rule says if you have the log of a quotient, you can go that way, but if you have the difference of two logs, you can turn it into a quotient. So that means that I can rewrite this as the log of base b of 64 over 16, right? And so I can simplify that as the log base b of, well, 64 divided by 16 is 4, and I've simplified that. All right, excuse me just 1 second, if you would. All right. Sorry about that. I don't know how to pause this recording, so okay. Let's look then at this. Should just type this. Write the following as a sum or difference of logarithms. Right. So if I'm given something like, say, the log base a of, let's say that we have a cube root of a squared b over c to the fifth, right? Okay. Well, the first and foremost, the thing that I would do first here is take this third root and call it a 1/3 power. So I have log base a of this a squared b. Oh, maybe a was a bad choice down here. No, sorry, that wasn't my choice. It was in the question. Over c to the fifth, all to the 1/3. Right? And the first thing that I can use is that power, right? This 1/3 can come down as a multiplier in front. And so I'll write this now as 1/3 multiplied by the log base a of a squared b over c to the fifth, right? But it's important to note that this 1/3 is multiplied by that and anything that that turns into, right? That's important to note. Because when I turn this log base a of a squared b over c to the fifth, I can break that up using the quotient rule. This becomes the log base a, and I'll say it as a squared b minus the log base A of C to the fifth. But again, that 1/3 is multiplied by all of this, not just, if you just leave it just like this as multiplied by that log base A of A squared B, you're now wrong. It's not the same thing anymore. It has to be multiplied by whatever that thing turns into, which is now that difference, right? Furthermore, this right here, this first log expression is a product that I can break up. And so I still have this 1/3 hanging out here, multiplied by what happens here. Well, this is now the log base A of A squared plus the log base A of B minus the log base A of C to the fifth, right? Now, these guys, I can simplify, well, I can simplify this one by taking that fifth down. But at the same time, I'm going to take this 1/3 and kind of just distribute it through so I can get rid of these parentheses. So let me do both of those things at the same time. I've got 1/3 now log base A of A squared. But in fact, this squared can come down as well. So if I multiply it out front, that just turns this into a 2/3. The 1/3 multiplies in here and gives me 1/3 log base A of B, and then minus right here, 1/3 gets multiplied by 5, so I have minus 5/3 log base A of C. There's one last thing that I can simplify here, and that's because my first log is log base A of A, right? What is that? Well, that is 1, right? Because this is essentially saying, what power do I need of A to get A? Well, I need the power of 1. So log base A of A is 1 will always be the case. And so this is then just 2/3 plus the rest of this stuff. 1/3 log base A of B. I can't do anything with that because I don't know what A and B are. And then minus 5/3 log base A of C. And we're done. All right. Let's look at this other one in the same little section. I've got log base B of A y to the fifth over m to the third n to the fourth. And it's the same thing, it just wants us to break these up, right? So you can do this bit by bit. I can say that this is going to be the log base B of A y to the fifth, the numerator, minus log base B of m to the third n to the fourth, and then use the product rule here and here, right? This turns into the log base B of A plus the log base B of y to the fifth. And then be careful with this y, this minus, because it applies to this entire log and anything that that log turns into. And so it's minus the log base B of m to the third, and also minus base B of n. I have some exponents that I can take out front, so I will. And that'll be the last thing that I can do here. So in the end, this turns into the log base B of A plus 5 log base B of y minus 3 log base B of m and minus 4 log base B of n. And they're broken up, and I'm done. All right, let's go the other way with some of these. Write this expression as a single or a logarithm. So we're going to go the other way and compress it down. Let's say I have 5 log base b of x minus the log base b of y plus 1/4 log base b of z. The first thing I want is any numbers in front, any multipliers, I want those to come up using that power rule and be exponents. So I'll write this as log base b of x to the 5th. And I'll write this other one over here as log base b of z to the 1/4. You could also write this as log base b of the 4th root of z, because that's what the 4th power means. This other guy, minus log base b of y, there's no coefficient in front, so you don't have to worry about it. And so I have this. But now, anything that's positive, right? This is a positive log. This is a positive log. Those are going to be in the numerator using the power rule. So I can actually do this in a bunch of steps if I wanted to. I can combine these two and say that this is now the log base b of x to the 5th times z to the 1/4, or the 4th root of z. And then I still have this minus log base b of y. Then I use the quotient rule because I have the difference of two logs, and I write this as a quotient. Log base b of x to the 5th, z to the 1/4, all over y. And that's it. Okay. So if I see something that looks like this, if I see log base a of a to the 5, right? Well, I know that using the power rule, I can say that this is 5 multiplied by the log base a of a. But log base a of a is 1, so this is 5 times 1, or just 5. And so I can actually generalize that if I have anything of this form, log base a of a to the b is going to simplify down to b. Likewise, kind of on a similar note here, if I have a raised to the log base a of x, what does that equal? Well, I don't know. Let's call this y for now and figure out. I want to figure out what y is. But to do that, I'm going to rewrite this as an exponential, right? Or as a logarithm, right? So this exponential up here is a logarithm, but think of this as like a to the b equals y for a moment. To write this as a log, I get b, the exponent, is equal to the log base a, the base of the exponent, of y, right? But b, I was just substituted as the log base a of x. And so this becomes, if I resubstitute the log base a of x, that's equal to the log base a of y. But for this to be true, it's simply that x is equal to y. Because if x is equal to y, then the log base a of x equals the log base a of x, and that's true, right? So I can again generalize that if I have something raised to the log with that same base of anything, it simplifies down to just x. So this is a formula, this, this is a formula sheet, I suppose, right here. It's worth, and I'll screenshot that. I'll try to make it not goofy. There we go. That's worth having. That's the properties that we talked about. We just talked about these two down there, but we've talked about all of these throughout the session. So that is on page something, book 354, if you want to see it. If you go into the ebook ever, that's where it is. All right. That's it for section 5.4. Again, please let me know if you have questions. I appreciate you guys dealing with this weird Wednesday movie stuff again, but there it is. Shoot your questions my way and have a good one. I'll see you all again on Monday. Bye.